Welcome to Learn a Lotl. My name's Nate, and in this video we're going to explore three seemingly different ideas and the fascinating connections between them. We're going to be looking at expanding binomials, Pascal's triangle, and combinations. This video is going to be in 4 parts. We're going to cover the relationship between the coefficients of a binomial and combinations. How many ways can I choose k objects from a group of n? Then we're going to look at the connections between combinations and the structure of Pascal's triangle. And finally, we're going to relate some structural elements between Pascal's triangle and binomial expansions. Then, finally, we will use what we learnt to prove the binomial theorem by induction. There's a lot to do, so let's get into it. To start, let's have a look at the different patterns we're going to see in this video. So, for expanding binomials, we see this very interesting pattern emerge. So let's start with x plus y to the power of 0. That's just 1. X plus y to the power of 1 is x plus y. X plus y squared is the perfect square, so we get x squared plus 2xy plus y squared. Then x plus y to the power of 3, you might want to check yourself, but you can definitely, if you want, check that just by expanding x plus y outside of x squared plus 2xy plus y squared. But what you'll find is that that is x cubed plus 3x squared y plus 3xy squared plus y cubed. And the general expansion we're working towards, this binomial theorem that we're going to prove in this video, is x plus y to the power of n gives us, in sigma notation or summation notation, we have our index k range from 0 up to n. The coefficient is given by n choose k, and I'm going to use that notation for n choose k. X to the power of n minus k, y to the power of k. And feel free to have a look at that sigma notation and compare it to these expansions we may have just done by hand, so that you can convince yourself that that is a way of writing the pattern we've seen so far, and then we're going to prove that that pattern persists. So this is one of the patterns we're looking at, this binomial expansion. And it relates very closely to another pattern, Pascal's triangle. And Pascal's triangle, we start with 1 and then 1, 1, and we kind of build a triangle from numbers essentially where the edges are always 1, and then any middle term is the sum of the 2 diagonally immediately above it. The 2 numbers diagonally immediately above it. So we'd get a 2 here. And then the next row would be 1. We'd have 1 plus 2, 3. 2 plus 1, 3. And then a 1 on the end. And then the next would be 1, 4, 6, 4, 1. And what you'll notice is here, the coefficients, so there's a 1 there and a 1 there, the coefficients of our binomial expansion actually match up exactly with Pascal's triangle, which is very, very cool. So already, if you want to expand a binomial to a power you're not used to, like 3, 4, 5, 6, 7, so on, but one that doesn't, it's not too big, like 86 or something, you could quickly draw up Pascal's triangle to figure out the coefficients, and then the pattern is just you start with the highest power of x, and for each successive term you kind of give one of the powers of x over to y. So x cubed here becomes x squared y to the 1. and then it becomes x to the 1, y to the 2, so on. So that the powers of x and y follow a very predictable pattern, but the coefficients are slightly less predictable. But knowing this connection, you can just draw a Pascal's triangle. So that's a nice trick we've learned already. The third pattern we have here that shares a close relationship is the fact that n choose k is the way we write this coefficient in the general case for the binomial expansion. And we've seen that the coefficients of the binomial expansion also appear in Pascal's triangle, which kind of tells us that Pascal's triangle and the binomial expansion also relate to combinations. So we have this n choose k. How many ways can you combine k objects from a group of n? You may have seen this written as nck or ncr, and I'm using this notation where it's kind of n over k, but without any fraction line. And there's a formula for it too, which is n factorial over k factorial n minus k factorial. But we're going to stick to this kind of intuitive idea that it's about choosing or creating combinations. So this is combinations. The order doesn't matter. It's just how many ways can I pick k objects from a group of n objects, where the order in which I pick those k objects doesn't matter. If the order mattered, I'd use permutations, but here we're using combinations. So we're going to investigate how on earth these three ideas are linked. And in doing so, we're also going to prove the binomial theorem, which is this guy here. So without further ado, let's jump into it. Firstly, we're going to consider how the coefficients of the binomial expansion relate to this n choose k combinations. And we're going to do that with an example. So let's consider x plus y to the power of 5. Now, x plus y to the power of 5 is x plus y multiplied by itself 5 times. Now, if we want to know what is the coefficient of the x squared y cubed term, really we want to ask how many ways from these 5 factors of x plus y can I pick 3 y's and 2 x's? So what I really mean by that is kind of in the same sense where when I expand x plus y squared by hand, each term in that expansion comes from me combining 2 elements. So when I pick x and x, I get the x squared term. When I pick x and y, I get an xy term, but I can do that twice. I can pick the x in the first factor and the y in the second, or I can pick the y in the first and the x in the second. So I get 2 xy, and then there's only one way I can pick the y in both factors, so I get 1 y squared. We're going to do that same process here for the power of 5, so I ask what's the coefficient of the x squared y cubed term? It's going to be the number of I'm going to say ways, which is a very general term, really, number of combinations, number of choices, whatever term you like, kind of the same thing we did here. Keep that in mind. So the number of ways I can pick 3 y terms and 2 x terms from my factors. where these are my factors. And we note that, again, in this, we have a restriction that we have to pick a term from each of the factors. We have to pick, in this case, a term from both. Here we're going to, for each expansion, we have to choose 5 terms total. So if I want x squared y cubed, if I pick 3 y's and I don't pick any more y's, I have to choose 2 x's because I have to choose 5 terms total because there are 5 factors there. So picking 3 y terms and 2 x terms is actually the same thing as just picking 2 x terms or just picking 3 y terms, and then the rest have to be the other. So what I realize is that the number of ways I can pick 3 y terms and 2 x terms from my factors is the same as saying how many combinations of 3 objects out of a group of 5. How many combinations are there of 3 objects out of a group of 5? And again, it's combinations. Combinations, the order doesn't matter because, again, in this example, when I picked the x term and the y term and the y term and the x term, well, xy is equal to yx. In other words, multiplication commutes, which means the order doesn't matter, which means the order that I pick my y terms doesn't matter. So I'm really asking for, when I want to know the coefficient of the x squared y cubed term, that coefficient is going to be 5 choose 3, or in the notation I'm going to use for most of this video, 5 choose 3, which is 5 factorial over 5 minus 3 factorial times 3 factorial. So it's equal to 5 times 4 times 3 times 2 times 1, but the 1's not going to change anything. 2 times 3 times 2. There's going to be some cancellation, and I get 20 over 2, which is equal to 10. And if I quickly draw up a Pascal's triangle, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, I notice that in this this row I've drawn, this is my row for x plus y to the power of 5, because I start at 0 and then go 1, 2, 3, 4, 5. My x squared y cubed term is this one, because I start with x to the 5, and then I move to x to the 4, y to the 1, then x cubed y squared, and then x squared y cubed. So the coefficient is 10. So that's an example describing the relationship between the coefficients of the binomial expansion and these n choose k combinations. And really what that connection is that asking for the coefficient of a specific term in the binomial expansion amounts to asking for a combination. A combination is a very general concept. It's just how many ways can you pick a number of objects out of a larger group of objects. And these coefficients is a specific case of that question. We're asking how many ways can you pick certain y terms from a total group of x plus y factors. So really this connection is, they're the same thing because coefficients of the binomial expansion is a specific case of a combinations question. So that is our first relationship between these ideas. And next we'll look at how n choose k relates to Pascal's triangle. To describe the relationship between combinations and Pascal's triangle, I really want to draw your attention to one thing. So combinations are some quantity which is defined by two numbers, n and k. And those two numbers are natural numbers, because this is a question of counting, and whenever we're counting, we use natural numbers. Pascal's triangle is a structure of numbers which has a very interesting, a very clean, I would say, visual basis. It's very much, you look at each number and it's the sum of those immediately diagonally above it. So it has a nice visual structure to it. But what I want to draw your attention to is that if I wanted to describe any particular number in Pascal's triangle, any particular element of the Pascal's triangle structure, I really need two numbers to specify its location, because I need to specify which row it's in, which row in Pascal's triangle, and then once I pick my row, let's say I pick this row, I need to then specify how far along that row is it. And let's say I want to specify this number, so I need two numbers to specify its location. So already there's a bit of a connection here, because combinations are a quantity defined by two natural numbers, and Pascal's triangle, every number in Pascal's triangle structure requires two numbers to be described. So what I'm going to do is, as before, the row is going to start with 0 and go up from there. And along the row, the first number is the 0th, and then up from there. And this is for every row. Now what I want to do is point out that there are a few similar structures here. So if n is a natural number, I want you to note that n choose 0 and n choose n are the same, and they are always 1, no matter what number n is. I should also say, however, in this case, n, I'm going to label this natural numbers including 0, because I could have 0 choose 0. Just as an example, 0 choose 0 is perfectly well defined. It's equal to 1. That's another reason why I kind of using zeros to label the first position in Pascal's triangle makes sense here, because I'm teasing out a relationship with combinations, and combinations are built on factorials, which are totally fine for 0. 0 factorial is 1. Now, the crucial piece of structure to make sense of in Pascal's triangle is this visual concept that the elements immediately diagonally above an element define that element. And that is going to be how we're going to tease out this relationship between combinations and Pascal's triangle. We're going to actually show that that is also a property over here for combinations. So in this example, I want to show, or in this example, we see that 6 is 3 plus 3. So the element in the fourth row, second position, is equal to the element in the third row, first position, which is this 3, plus the third row, second position, which is this 3. So in general, the structure of this, each term being defined by the immediately above diagonal elements, is the, let's say, the n plus 1th kth position, and I'm intentionally choosing n plus 1 because later on it will help out in our binomial theorem proof, is equal to the n k minus 1th position plus the n kth position. And now what I want to show is that n choose k minus 1 plus n choose k. Well, let's just write that out and see what happens. We get n factorial over n minus k minus 1 factorial, k minus 1 factorial, plus n factorial n minus k factorial k factorial. And if I bring that onto a common denominator, I get n factorial k plus n factorial n minus k plus 1, because this term n minus k minus 1 is n minus k plus 1, over n minus k plus 1 factorial k factorial. And that is equal to n factorial n minus k plus 1 plus k. There's going to be a cancellation in those k's. And then I'm going to rewrite that as n plus 1 minus k factorial. And I notice that on top in that numerator we have n factorial times n plus 1. So that's the same thing as n plus 1 factorial. And then I notice that that's over n plus 1 minus k factorial, which is equal to n plus 1, choose k. So what we've shown here in this calculation is that this structure, which we wrote out from what we noticed in Pascal's triangle, so the Pascal's triangle structure, that we have these triangles where the outer terms are just 1, which is also the case for combinations, and the inner terms are defined as the sum of the numbers immediately diagonally above them. We wrote that out. This is algebraically that diagonally above sum structure, and we found that that structure is also the case in combinations. So really what we found here is that Pascal's triangle, which is really kind of a visual structure, it looks nice. If we break it down to an algebraic structure, what that structure is combinations. So that is why combinations and Pascal's triangle also seems to give us the same information. The last similarity I want to draw a bit of attention to between Pascal's triangle and binomial expansion is also along these ideas of how the previous row in Pascal's triangle influences the next row, and how the previous binomial expansion influences the next one. So if we consider x plus y to the n plus 1, it's x plus y times x plus y to the n. So, for example, let's choose n equals 3. X plus y to the n plus 1, which is 4, is x plus y times x plus y cubed, which is x plus y times x cubed plus 3x squared y plus 3xy squared plus y cubed. And now we consider how we get certain terms in this expansion. So to get the x squared y squared term, really what we do is we have the 3x squared y term times y plus the xy squared term, the 3xy squared term, times x. So we add y times 3x squared y plus x times 3xy squared, which gives us 6x squared y squared. And what I really want you to notice there is that in order to produce this x squared y squared term, which would be the 0, 1, 2, the second term along this fourth row, to get that second term, we added the x squared y and the xy squared term of the third row, which if we think about it, along the third row, we have the zeroth number along the third row is the x cubed term. Then the first, second, third, we have the x squared y and the xy squared. So in order to get the second number along the fourth row, we added the first and the second number along the third row, which also links to that combinations result we just proved. But it also has this interesting relationship between Pascal's triangle and the binomial expansion, which really is all about how that next row is influenced by the previous row. And here, that's really how each successive expansion is very much built on the previous expansion. All right, so we looked at some very interesting connections there, and now we're going to get to the proof. We want to prove the binomial theorem. So what do we actually want to prove? The thing we want to prove is that for all natural numbers n, we want to prove that for all natural numbers n, we have x plus y to the n is the same thing as this sigma notation. N choose k, x to the n minus k, y to the k. And we're going to prove this by induction, which seems the natural choice because we're dealing with a statement that needs to be true for all natural numbers. So we have our base case. Technically here the base case is n equals 0, which is a very, very simple base case. And that is indeed equal to this, because if I write out this sigma notation using n equals 0, I only get one term. I get 0, 0, x to the 0, y to the 0, which is just 1, which is true. And just to be sure, I'm also going to write n equals 1. I don't need to. N equals 0 covers this proof as a base case, but I will also write the n equals 1 case just so you see it. So that is actually going to also be this, because if I write out that notation, I get 1, 0, x to the 1, y to the 0, plus 1, 1, x to the 0, y to the 1, which is x plus y. All right, and then we do our induction step. So the induction step is we suppose there exists some natural number, let's call it m, such that this claim is true. We already know that for m equals 0 and m equals 1, this is the case, but here all we need to do is assume it's the case for whatever this number m is. It doesn't really matter. And now we want to show that this is also true for m plus 1. So we want to show this statement. That's what we want to show for induction. And we will do that over the page. So I've copied in that statement from before. This is the statement we want to prove for induction. So let's start. X plus y to the m plus 1, which is our left-hand side, is equal to x plus y times x plus y to the m. And we actually know by our induction step, we assumed that the thing we're trying to prove is true for m, which means I can write this. And I might write by induction step, just to let you know why I've done that. and why I'm allowed to do that. So we have, if I just expand out that bracket there, x times this big sum plus y times the very same big sum next is going to be the guts of the proof. How are we going to exploit what we've learnt through these connections between all these different ideas to prove this statement? Where do we go from here? I encourage you to pause, take a breath, meditate, pause and ponder on it for a bit, and feel free to come up with a plan of action and go on with the proof if you want. So what I will do for the next step really is exploit that structure we talked about earlier where the end terms are always that 1 and the middle terms are defined by that additive structure. So that's what I'm really going to exploit here. So my next step, what I'm going to do is remove those end terms primarily so I can focus on how the middle terms are defined by that relationship we explored earlier. So if I remove the end terms, I get x to the m plus 1. Now I got the x to the m from here, specifically the k equals 0 term. So now I'm going to add that sum back in, and I'm actually going to multiply the x inside the sum now. So I have k equals 1 because I removed the k equals 0 term, and I have mk x to the m plus 1 minus k, y to the k. And I'm going to remove, again, that end term, which is y to the m plus 1. And I got that y equals m from the k equals m term here. So what I'm left with is this sum from k equals 0 to m minus 1 because I took the m term, and I have m choose k, x to the m minus k, y to the k plus 1, because I've gained a y term there, because I took that, I put that y inside the sum in that step also. Okay, so I've got these end terms that I've pulled out, and now what I want to do is I want to relate these middle terms. The way I want to relate them is I actually want to bring them together under one summation. But they don't really match up. I have this sum from k equals 0 to m minus 1, and this sum from k equals 1 through to m. So the way I'm going to fix that and proceed is I'm actually going to redefine my index of summation. I'm going to let j equal k plus 1 so that this sum becomes j equals 1, because k equals 0 means j equals 1, up to m, because if j equals k plus 1 and we go up to m minus 1 for k, that means we go up to m minus 1 plus 1 for j. And then m, this has to be j minus 1, x to the m minus j minus 1, y to the j. So that is my corrected sum. And now over the page, I'll rewrite this statement. So keep this statement in mind. If you're following along on paper, great job. That's a good idea. But keep this statement in mind. Over the page, I'm going to rewrite that statement, but with this new summation term. So from before, we have this x, m plus 1. We have this sum from k equals 1 to m choose k, x to the m plus 1 minus k, y to the k, plus this sum in terms of j equals 1 through to m, of m choose j minus 1, x to the m minus j plus 1, y to the j, and then that yn term. Now I'm going to bring these two sums together, and I'm allowed to do that because k and j are these summation indices. They're not, I could just redefine j as k. It doesn't really matter what symbol I use there. So the point is that these sums match up. They're both sums from something equals 1 up to m. So I can bring them together. So when I do that, I get x m plus 1 plus 1 sum from k equals 1 to m. I also notice that these x and y terms actually match up, so I can factor those out. So I get m choose k plus m choose k minus 1 times m plus 1 minus k, y to the k, and then that y m term, n term. Then what I notice is that this, I actually know the value of that from earlier when we were exploring the similarities between combinations and Pascal's triangle. I know that this sum is the same thing as m plus 1 choose k. So I can rewrite this as x to the m plus 1 plus this big sum from k equals 1 through to m of m plus 1 choose k, x to the m plus 1 minus k, y to the k, plus y to the m plus 1. And then what I'm going to do is add back in those n terms. Because, of course, x to the m plus 1 is the same thing as for this sum but with k equals 0, and this y to the m plus 1 term is the same as for this sum if I went up to m plus 1 instead of m. So this is the same thing as the sum from k equals 0 to m plus 1 of m plus 1 choose k, x to the m plus 1 minus k, y to the k. And that is what I wanted to prove for my induction. So, by the principle of mathematical induction, our proof is done. We have that the statement is true for n greater than or equal to 0. Thanks for watching. I hope you enjoyed that video. I just wanted to say that I've added a suggestion form in the description of this video, and I'm going to add that to the description of all my videos. It's a link to an anonymous Google form. You can give ideas, suggestions, feedback, anything you'd like me to hear about. I'm very keen to keep going and improve my style, so I'm very receptive to any feedback you have. Also, don't forget, if you enjoyed the video, give it a like, give it a subscribe, tell your friends, tell your pets, tell everyone. It really helps. So thank you again. And until next time.